Welcome to Understand the Math. In this Calculus 1 video, we're learning how to differentiate trigonometric functions. We'll begin by reviewing two important trigonometric limits that form the foundation for finding these derivatives. Then, we'll walk through the derivation of the derivatives of sine and cosine step by step so you can see exactly where these rules come from. Finally, we'll summarize all 6 derivatives, practice applying them to examples, and even find the equation of a tangent line using trig derivatives. Be sure to download the free guided notes to follow along and work through the examples with me. We're going to look at two fundamental trigonometric limits and walk through some examples. The first limit that we'll look at is the fundamental sine limit. This is the most important trigonometric limit, and it provides the foundation for finding the derivative of the sine function. This fundamental limit is the limit of sine theta divided by theta as theta approaches 0 and is equal to 1. I think this limit can be best understood if we look at the graph of sine theta and theta. On the right, I have graphed sine theta and theta. As theta gets close to 0, that's in this region and in this region, you can see that the two graphs are virtually the same. That means that they're about the same number, and when we divide two numbers that are the same, we are going to get the value of 1. So this limit is equal to 1. Let's now walk through some examples where we are going to find the given limit. Here's our first example. We want to find the limit of sine of 5x divided by 3x as x approaches 0. The first thing that you always want to do whenever you're given a limit is substitute in the value. So let's go ahead and let's do that. If we let x be 0, we get sine of 0 all divided by 0. Sine of 0 is 0, so this limit is 0 over 0, which is called an indeterminate form. When you're solving any limit that has a sign in it, you want to utilize the fact that the limit of sine theta over theta as theta goes to 0 is equal to 1. If we look at our limit, I want you to focus on the 5x right here. Think of the 5x as theta. So we need to have a 5x in the denominator. So we can say that this is the limit as x goes to 0 of sine 5x all divided by 3x, and we're going to multiply by 5 over 5 because we can't change the problem and just divide by 5. Now what we're going to do is we're going to shift this 3 and this 5. And we're just going to rewrite this as the limit as x goes to 0 of sine 5x all divided by 5x times 5 over 3. We now know that this limit is equal to 1 because it's just like sine theta over theta. So we have 1 times 5 over 3, so we get an answer of 5 over 3. And that's what our limit is equal to. Let's now work through our second example. This one's a little bit harder than the first one. This is the limit of tangent 6x divided by sine 2x as x approaches 0. Just like we did for our first one, we are going to start by substituting in that x is equal to 0. So this is tangent of 0, all divided by sine of 0. Tangent of 0 is 0, sine of 0 is 0, so we again have the indeterminate form 0 divided by 0. Since we don't have a formula for a limit with tangent, I think the best way to solve this problem is to let tangent of 6x be sine 6x over cosine 6x. So we can write this as the limit as x goes to 0, sine of 6x, all divided by cosine 6x, and then all of that is divided by sine of 2x. Now you can see that we have a sine 6x on top and a sine 2x in the denominator. To evaluate these limits, we need to divide sine 6x by 6x, and we need to divide sine 2x by 2x. So what we're going to do in our numerator is we're going to multiply this by 6x divided by 6x, and then in the denominator, we're going to multiply by 2x over 2x. Let's see what this gives us. This gives us the limit as x goes to 0, sine 6x over 6x times 6x all divided by cosine 6x. We're just changing around terms. And then in our denominator, we have a sine 2x divided by 2x times 2x. This limit is going to go to 1, and this limit is going to go to 1. And then notice that our x's cancel out. So what we're left with is the limit as x goes to 0 of 1 times 6 divided by cosine 6x, all divided by 1 times just 2. Cosine of 0 is equal to 1, so this is just 6 over 2, which is equal to 3. And 3 is the value of our limit. Let's now go over the fundamental cosine limit. This limit is also used for finding the derivative of the sine function. This fundamental limit is the limit of 1 minus cosine theta divided by theta as theta approaches 0, and the limit is equal to 0. I think this one is a little bit harder to memorize than the sine one, so you may have to spend some time memorizing it. This limit can be derived algebraically by multiplying by the conjugate of the numerator and then using the fundamental sine limit. I am not going to go through that in this video, but if you want to do it, I'm sure you can do it if you follow these directions. What we're going to do now is walk through an example where we find a given limit. The limit that we are going to evaluate is the limit of 1 minus cosine x divided by sine x as x goes to 0. Let's begin evaluating this limit by just substituting in that x is equal to 0. So we have 1 minus cosine of 0 all divided by sine of 0. Cosine of 0 is 1, so we have 1 minus 1 over 0, which gives us the indeterminate form 0 divided by 0. To evaluate this limit, we have to use two things. The first limit that we can use is the limit as x goes to 0, sine x all over x is equal to 1. And then the one that we just saw above, the limit as x goes to 0 of 1 minus cosine x, all divided by x is equal to 0. When you look at the limit that we've been given, 1 minus cosine x over sine x, you can see that it's similar to these two limits that I just wrote down, but there's no x there. So I think the best thing that we can do to evaluate this limit is divide both the numerator and the denominator by x. Let's go ahead and let's go down here. I'll draw a little arrow here, and let's do that. So this is the limit as x goes to 0 of 1 minus cosine x all divided by x, all divided by sine x divided by x. We can do this algebraically because we're dividing both the numerator and the denominator by x. So it's just like multiplying by 1. You can see then that our top limit, 1 minus cosine x over x, is going to go to 0. So let's just put an arrow here. That goes to 0. And then our limit on the bottom is going to go to 1. So we'll say that goes to 1. So our answer is 0 over 1, which is 0. And that's what our limit equals. Let's now learn how to find the derivative of sine and cosine. We're going to start by finding the derivative of sine x. We are given the function f of x is equal to sine x, and we want to find f prime of x. We are going to find f prime of x by starting with the limit definition of the derivative. It's the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. Now we're going to substitute in that our function is sine x. So we have the limit as h goes to 0, sine, and then instead of x, we're going to plug in an x plus h, minus f of x, which is sine x, all divided by h. Let's now look at this term. We can simplify this term using one of our trig formulas. That formula is sine of a plus b is equal to sine a times cosine b plus cosine a times sine b. Let's now substitute that in. We have the limit as h goes to 0. Sine of x plus h is now sine x, cosine h, plus cosine x sine h minus our sine x. And then all of this is divided by h. Let's now look at our numerator and see how we can simplify it. Notice that we have a sine x here and a sine x here. Let's go ahead and let's combine those two terms. This is the limit. As h goes to 0, we have sine x, and we're left with cosine h minus 1 plus cosine x sine h, all divided by h. Let's now look and see what we have. Notice that we have a cosine h minus 1 divided by h, and then a sine h divided by h. Those are actually two fundamental trigonometric limits, and their value is known. So let's do this. Let's split what we have into two pieces and pull out the sine x and cosine x because they don't have h in them. This gives us sine x times the limit as h goes to 0, cosine h minus 1 all divided by h, plus cosine x times the limit as h goes to 0 of sine h over h. This limit we know, and that limit is equal to 0. And then the other limit that we know is this limit right here, and that limit is equal to 1. So the derivative of sine x is just cosine x. I always like students to understand this graphically as well. So I have graphed up here in the upper right sine x and cosine x. Remember that the derivative is just the slope of the function. Let's look at our sine graph. At x is equal to 0, the slope is 1, and that's what cosine is equal to. Likewise, at pi over 2, the slope of the sine function is 0, and that's what cosine is. And that same process happens in the remainder of the graph. Cosine is the slope of sine, which is why the derivative of sine is cosine. Let's now look at the derivative of cosine x. I am not going to walk through the derivation. I'm just going to show you the formula. If our function f of x is equal to cosine x, then the derivative of cosine x is equal to minus sine x. Over here on our graph, I have graphed cosine x and minus sine x. When x is equal to 0, the slope of our cosine function is 0, and that's what minus sine x is equal to. When x is equal to pi over 2, the slope of our cosine function is negative 1, and that's the value of minus sine x. And that continues for the rest of the graph. And that's why the derivative of cosine x is minus sine x. We're now going to learn how to find the derivative of all 6 trigonometric functions and walk through some examples. I have listed the derivatives of all the trigonometric functions here in this table. Let's go over them, and I want to show you some patterns. The derivative of sine x is cosine x, and then the derivative of cosine x is minus sine x. Let's now look at the derivative of tangent x. It is equal to secant squared x, and then the derivative of cotangent x is equal to minus cosecant squared x. Those two derivatives are really similar in structure, and you just have to remember that the derivative of tangent is positive and the derivative of cotangent is negative. Let's go over our last one. It is the derivative of secant x, and it is secant x tangent x. In a similar way, the derivative of cosecant x is minus cosecant x cotangent x. Notice that the derivative of all the trig functions that start with the letter c have a negative sign. When you go to memorize these, I would suggest memorizing the 3 on the left, the derivative of sine x, tangent x, and secant x, and then the derivatives on the right just follow from those in structure, except that they have a negative sign. When you take derivatives of trig functions, you often have to simplify them. And when you're doing the simplification, you often need trigonometric identities. So I've just listed the 3 trig identities that you can use for simplification right here, just to make it easier. Let's now walk through some examples where we are going to differentiate the following functions. In our first example, we have f of x is equal to x squared times sine x. Notice that this function has 2 pieces, the x squared piece and the sine x piece. So when we take the derivative, we are going to have to use the product rule. Let's go ahead and let's do that. F prime of x is the first term, x squared, times the derivative with respect to x of our second term, sine x, plus our second term, sine x, times the derivative with respect to x of our first term, which is x squared. Now we get that our derivative is x squared, the derivative of sine x is cosine x, and then we have sine x times the derivative of x squared, which is 2x. Notice that we can pull an x term out from both of these. So we can write this as x times x cosine x plus 2 sine x. And that's our derivative. Let's now look at our second example. In this example, we are also going to need to use the product rule because we have a first function and a second function. Our derivative, f prime of x, is equal to our first function, e to the x, times the derivative of our second function, which is cosine x, plus our second function, cosine x, times the derivative of our first function, e to the x. We now have e to the x the derivative of cosine x is minus sine x. And then we have cosine x times the derivative of e to the x, which is just e to the x. Notice that we have an e to the x term common to both terms, so we can pull that out in front. And we're left with e to the x times cosine x minus sine x. And that's our derivative. Let's now look at our third example. This example also has two functions. The first function is secant x, and the second function is tangent x. Our derivative then is our first function, secant x, times the derivative of our second function, tangent x, plus our second function, tangent x, times the derivative of our first function, which is secant x. This now gives us secant x times the derivative of tangent, which is secant squared x, plus tangent x times the derivative of secant x, which is secant x, tangent x. Now let's see what we have in common. Looks like we have a secant x common to both terms, so we are going to bring that out. So this is secant x, and we're left with secant squared x plus tangent squared x. And that's our final answer. In our fourth example, we have a function, f of x is equal to sine x divided by 1 plus cosine x. This function has a numerator and a denominator, so it is a quotient, and we can use the quotient rule. Our derivative, f prime of x, is going to be the bottom term, which is 1 plus cosine x, times the derivative of our top term, sine x, and then we have to subtract off our top term, sine x, times the derivative of our denominator, which is 1 plus cosine x. And we're going to divide all of that by 1 plus cosine x quantity squared. I think one mnemonic that might help remember this is thinking of the top term as the high term and the bottom term as the low term, and then the derivative is just low d high minus high d low, all divided by the square of what's below. Let's now go ahead and simplify this. This is 1 plus cosine x. The derivative of sine x is cosine x. And then we subtract off sine x times the derivative of 1 plus cosine x, which is just minus sine x. And all of this is divided by 1 plus cosine x quantity squared. Now let's go ahead and let's multiply things out. Our first term gives us cosine x plus cosine squared x. And then our second term, we have a minus sine x times a minus sine x. So that gives us a plus sine squared x. And then we have our same term in the denominator, 1 plus cosine x quantity squared. Let's now look at this expression, cosine squared x plus sine squared x. That is a trigonometric identity, and that is equal to 1. So we have on top cosine x plus 1, and then we have a 1 plus cosine x quantity squared in the denominator. Those terms are the same, so one of them cancels out, and we're left with 1 all divided by 1 plus cosine x. And that's our final answer. Let's now look at another type of example. In this example, we are going to prove that the derivative of secant x is equal to secant x tangent x. These proofs are really common when you're in a calculus course and learning about trig derivatives. I think the hardest part of a proof is figuring out where to start. The first place to start is by thinking about a function that is similar to secant x that we actually know the derivative of. And that function is going to be cosine. So we're going to start by saying that the derivative with respect to x of secant x is the derivative with respect to x of 1 divided by cosine x, because secant x is 1 divided by cosine x. Notice that this function has a numerator and a denominator, so we can find the derivative using the quotient rule. So we have the bottom term, which is cosine x, times the derivative of our top term, which is 1, minus our top term, which is 1, times the derivative of our bottom term, cosine x. And then we're going to divide all of this by cosine x quantity squared. The derivative of 1 is equal to 0, and the derivative of cosine x is minus sine x. So this gives us minus sine x, all divided by cosine x squared. So this is sine x divided by cosine x squared. Let's go back up here to the top. I'm going to put a red check here. We are looking for our answer to be secant x tangent x. So let's divide up sine divided by cosine x squared into two pieces. We can divide this up like this. Sine x divided by cosine x times 1 over cosine x. And that gives us tangent x times secant x. Let's then rewrite this as secant x tangent x. And we have proved that the derivative of secant x is secant x tangent x. Let's look at one last example. In this example, we are going to find an equation of the tangent line to the curve y is equal to sine x plus cosine x at the point 0, 1. Let's begin by writing down the equation of a general tangent line. That is y minus y1 is equal to our slope times x minus x1. Our point x1, y1 is going to be the point 0, 1. And now we just have to find the slope. The slope of the tangent line to the curve is the derivative of our curve, dy dx, evaluated at the point x is equal to 0. Let's now go ahead and find the derivative. The derivative is the derivative with respect to x of sine x plus cosine x, and we're going to evaluate that at x is equal to 0. The derivative of sine x is cosine x, and then the derivative of cosine x is minus sine x, and we're going to substitute in that x is equal to 0. This gives us cosine of 0 minus sine of 0. Cosine of 0 is 1. Sine of 0 is 0, so our answer for our slope is 1. Now we can take this value and plug it back into our equation, and then also plug in the point 0, 1 in for x1 and y1. This gives us y minus y1, which is 1, is equal to our slope, which is 1, times x minus x1, which is 0. So we have y minus 1 is equal to x, and that gives us the equation y is equal to x plus 1. And that is the equation of the tangent line to the curve y is equal to sine x plus cosine x at the point 0, 1. And that's it. You've learned the key trigonometric limits, how to derive the derivatives of sine and cosine, and how to use rules to differentiate all 6 trigonometric functions. You also practice using these derivatives in examples and finding the equation of a tangent line to a trig function. To really master these ideas, make sure you work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.